This is section 3.2, and what I want to do is we're going to briefly review the exponential function. I want to discuss what the inverse of f of x is, and we're going to define what the log is, and we're going to see, I hope, that the inverse of, if this is f of x, then the inverse is the log. Okay. So the first thing I want to do is just to focus in on the function y equal a to the x, and we're going to use where a is greater than 1. And generally, well, not all the time, but often, we're going to have three choices for a. A will be equal to 10. A will be equal to that number e, which is about 2.17128. 1828. Oops, forgot about that. 2.17 is what matters. Let's think of it as that. And then a is equal to 2. Okay. These are really common law bases. This is used, E is used in finance, business, math, and science. 2 is going to be used in computer science. And then this is sort of customary. So it's just custom that we use that one. So again, when we looked at the graph of a to the x, and I'll use y equals 10 to the x, just as an example. The graph is somewhat like that. We'll look at a picture in a second. This is going to always be the point 0, 1. Okay, we'll see that as x approaches minus infinity, that y approaches 0 from above. So y equals 0 is a horizontal asymptote. We'll see that as x goes to infinity, 10 to the x does. So in other words, as the exponent goes to infinity, so does 10 to the exponent. So does 10 to the exponent. Okay. And we're also going to see a couple of other things about this. The domain is equal to all real numbers. And what that tells us is that a to any power is valid. So for example, if we had 10 to the minus 3, that would be 1 over 10 to the 3. And we saw that 10 to the 0 is 1. That's what the domain tells us. And then the range is going to be not including 0, but 0 to infinity. And what it tells you that a to any power is positive. Okay. So I want to get mathematical on you, and then we'll get practical. So again, here's the graph, y equal 10 to the x. And we see that it's 1 to 1. That means that f of x is equal to f of y. So 10 to the x equals 10 to the y, if and only if x is equal to y. That's what 1 to 1 means. And 1 to 1 also means that it has an inverse. And I wanted to review inverses just a little bit. I think that'll help us understand. And then I want to convince you why we want to have an inverse. So I'm going to look at a question, f of x, 3x minus 9. And we want to see what the inverse is. And what the inverse does is that you start with x, you add 9, and you divide by 3. So this is what the inverse would look like. Okay. And if we wanted to solve 3x minus 9 equals 135, we could do it directly, but we could also just plug this number into the inverse. And that will give us the solution. Let's see what happens. We get 135 plus 9 over 3. That's 144 over 3. And so that is going to be equal to 48. Okay, now let's check to make sure. I'm saying that plugging the answer into the inverse gives us the solution. Let's see if that's true. So we do 3 times 48, and I subtract 9. I should be getting 135. Well, 3 times 48 is going to be 144. And I subtract 9, and that's going to be 135. Okay. So sorry about that. Just want to get rid of that. So this is a weird thing. We really haven't talked about that before. But if I want to solve an equation, I can plug the answer into the inverse, and that'll give me the x that solves the equation. So keep that in mind. That's very important. Okay. So here's an example that we're going to look at a couple of times. Let's say we have this function p of t, and p of t is going to be an investment of $1,000 at 10% compounded annually. Now, interest is almost always annual, so sometimes people just say interest. So again, the function is going to be what you invested, 1 plus the rate to the t. Now, our rate is 10%, but if we write it as a decimal, we move the decimal over to 2, and the way we write it as a decimal is 1, 0, which is just going to be 0.1. So I'm going to write that. It's 0.1 to the t, just to simplify it, 1,000. Okay, that took a lot of work. Okay, and I'll tell you why. Okay, so we want to analyze this investment. And one of the tools in analyzing investments is when does it double? And so we're going to say, when does P of t, the investment, double? And so that would mean that we would want to solve P of t equals 2,000. In other words, we want to solve 1,000, 1.1 to the t equaling 2,000. Okay, so now let's just say we're magically given what the inverse is. If we know P inverse, let's just say we're given that, P inverse of 2,000 would give us the t solving 1,000, 1.1 t equal 2,000. That's what an inverse does. It gives you back the t you started with. We start with some t that doubles our investment. So we want to find out what that t is. Well, we find the inverse of p, plug in the number 2,000, and we're going to get back our answer. Now, it turns out we don't know what the inverse is yet, but it turns out that t is about 7.2, and you can check that if you want. So if you want to do that, just pause the video and check it. So we're going to come back to this, but I want to look more carefully at the inverse first. Okay, so we're going to come back to that answer. Okay, but by the way, this tells us that 7.2 years, $1,000 investment doubles, and again, that's about the rate of return of the stock market as a whole historically. Some years it sucks and you lose 10 or 20%. Some years you might gain 30%. So it's an up and down ride, but in the long term is what I'm talking about. Okay, so now I want to just look at some exponential functions. So here's one, f of t equals 10 to the t, and I want to look at what I want to do is I want to solve 10 to the t equaling 92. No real reason that I'm choosing 92. It's just kind of a random choice of numbers. So what I would want to do, I would find with this magical inverse. And what I would do is I would say, okay, I'll plug in my answer. And that's going to be equal to the exponent. Let me write down here, is equal to the solution of 10 to the t equal 92. So in other words, it's the exponent of 10 that yields 92. And what that is, let's see what that is. And later on, we'll see why that is. That's going to be t. If I can find this magical inverse function, and I plug in this number 92, and what I get is about one. It's really going to be more digits. I get about 1.96379, and you try it. Try 10 to this number and see what you get. Okay, so pause and try it. Okay. Yeah. What I got was this. So pretty close. So it's not exact, but it's pretty close. Again, I'll tell you how to get to that exponent. But what I want to do is just do a couple of things, and then we'll define what that exponent is. Okay. So I want to look next at this one, f of t equals 2 to the t, and I want to think about f of t. I plug in some t, and I get, let's say I get 90. No, I already did that one. I get 39. Okay, I don't know what that answer is. So let's say, again, I have this inverse. So I plug 39 into the inverse, and that's going to give me the exponent, t, that solves 2 to the t equals 39. In other words, it's the exponent of 2 that yields 39. Okay, and again, we'll look this up later. Okay, let me do one more of these. Another base is going to be f of t equals e to the t. And remember, e is this number, it's about 2.71828, 1828, and it just keeps going on and on and on. So keep in mind that's what that is. And let's say that I want to solve e to the t equals 10. Well, again, I have to find the magical inverse. Plug in 10. And I'm going to get t, and that t is going to be, that's going to solve e to the t equals 10. Okay. So the inverse, again, is the exponent of e that equals 10. Okay. So I'm getting to what the inverse actually is, but I'm getting tired of writing this. So here, let me look at this. I'm going to go speak generally. So f of t is a to the t. F inverse, let's say that's equal to some value y. F inverse of t is going to be the exponent of a that yields the exponent t of a, the exponent of a that yields y. Okay, now I get tired of writing that all the time. So what we're going to do is we're going to have a shorthand, and we're going to say, instead of writing the exponent of a that yields t, I'm going to write the log base a of t. Okay, that's what the exponent is going to be equal. And let me show you how you interpret this. Let's say I have the log, an expression, the log a t is equaling y. Okay, what this gives me the exponent of a that solves a to the y, a to the t equaling y. So the way that I remember this is when I see a log and I write that, I kind of make this kind of recycling circle, and a to the y equals t. Okay, so when I see this log, I immediately think of that. So I'm going to say it one more time. The log base a of t equaling y is the exponent of a that yields y. So let me give you a numerical example. We want to find the log base 10 of 92. And let's just call that y. That solves 10 to the y equal 92. So that number is going to be the solution to that. This number here, again, log 10 of 92. Log 10 of 92 is the exponent of 10 that yields 92. Okay. Now, so this I'm just trying to get used to the language. When you see the log, keep in mind that this is just the reverse of this. This log is the inverse of this. Okay. Now, the log is a tricky thing, and by that I mean that it is very hard to compute. And so what happens is that in the old days, people would have tables of logs. So you'd look up, like if you wanted to solve 10 to the y equaling 92, let's say, I would get out my table of logs, and I would plug this number in here, and I would get a digit. I would get a number that has several digits. I think we had this before, so I'm just looking back. It was about 1.96379. And again, what that number represents, 10 to that number, gives me 92. So 10 to this is going to give me 92, about 92. It's always going to be an approximation. Okay, so that's the old days. We don't do that anymore. What you do is you look to a website or your calculator. And your calculator is going to have two buttons. One of them is going to be log, and that usually stands for the log base 10 of whatever you plug in. Or you're going to have this key, ln, and ln is going to be the log base e, and again, you would take whatever base that does it. So that's what your calculator does. Or you can go to a website like Wolfram Alpha, or just Google and find some other calculators, and then plug in something like this, so log 10 of 92, and just see what you get. In fact, why don't you go do that just for fun? Just, Google this, see what you get. I'm going to go do it too. And I'll share the screen so you can see what I'm doing. Hopefully you went and did this. So again, let me go share. Sorry, so taking longer than usual, as usual. There we go. Okay, so I'm going to go log 92, and see, you can see it what it gives me. So I'm just going to hit it, and it gives me the answer. So you can see what it is. So the log is kind of easy to find. So what I'm going to do is just give you a few numbers to practice with the log, and then you can come back. So we're going to do, I want you to find the log base 10 of 810, and then I want you to put it into this equation. I want you to use that to solve that, and then try the natural log of 32, and that's going to solve e to the x equal 32. I'm going to give you one more. I'm going to give you the log base 2 of 55, and that will solve 2 to the x equal 55. Okay, so again, why don't you use this website or another one? I'm going to use this website, and I know it's hard to see, but here, let me stop the share, and then I'll come back so you can write them down. These are the 3 equations I want you to solve, and then we'll come back. So try to do that. Like I'm going to go back to that website I had and answer these, which you can watch. Okay. Okay. So I'm going to do log 10 of 810. Remember, for log 10, you don't write down, you don't have to write down that 10 in there. Let's see what I get. So you can see my answer. I get log 10 of 810 is about, let's go to 3 digits, understanding we're not going to get complete accuracy. And what that tells me, that solves 10 to the x equals 810. So my x would be 2.908. And you can check that if you want. I'll leave that something you can do. Let's solve the next one, natural log of 32. And that's going to solve e to the x equal 32. So let's see what happens there. So again, I'm just going to write natural log of 30. Did I get 30? Yeah, 32 is the number. See what I get. Okay, I get 3 point. Again, I'm just going to go to 3 digits and round. 3, 4, 6, 6 is my answer. And that's going to solve e to the x equal 32. So e to 3.466 is about 32. And again, you can check. And then the last one is going to be this one, log 2 of 55. And so the way I'm going to solve that is I'm going to write this log. I'm going to pretend I'm putting it on the bottom. Got it right here. And I get 5. I'm sorry, the log 2 of 55. I solved 32. I was thinking of the other problem. So the log 2 of 55 is about 5.781. And what that means is that 2 to the 5.781 is going to be just about 55. And again, you can check these. I'm not going to do it now. So I'm going to stop the share. And I have one more thing to say, and then I'll stop the video. So again, the way that I solved these equations was just the way that I solved this equation. Sorry, it freaked out on me for a second. The way that I solved this equation was to just use that command. The way that I solved this equation, I use that command. The way that I solved that equation, I use that command. Okay. So there's one last thing I want to do with inverses, and that'll be it. I'm going to go back to something that I wrote earlier, where I had the graph of y equals a to the x. It'll just take me a moment to locate. Okay, so here I'm just going. I want to use the x. Okay. Okay. So we looked at this. This was y equals 10 to the x, and that's what that looked like. And so what I want to do is look at the inverse. And remember, if f of x equals 10 to the x, f inverse of x is going to be the log base 10 of x. Okay. So let's see. What I'm saying here is that as x goes to minus infinity, in other words, as the exponent goes to minus infinity, the base goes to 0. So remember, we're going to switch the role of x and y. So what that's going to tell us for the log base 10 of x, as x approaches 0, so in other words, as that approaches 0, the exponent is going to go to minus infinity. And we'll verify this. So in other words, this point here is now going to be down here. We're switching the roles of x and y. Okay. And then notice here we said as the exponent goes to infinity, so does 10 to the exponent. So over here, the log base 10 to x, we're going to say x goes to infinity. So remember, x is the base, not the base, but x is the answer. So what we're saying that as x goes to the infinity, in other words, as whatever number we want the exponent for goes to infinity, what's going to happen is the exponent is also going to go to infinity. So so in x it says as 10 to the x goes to infinity, so does the exponent. For the log base 10, what we're saying as 10 to the x goes to the infinity, so does the exponent. So in other words, this point here, put it double star, is going to be up here, and the graph is going to go like this. And then this point here is going to end up over here. Okay. I might have spent a little bit too much time talking about that. Abstractly, if you got that, fine. If you didn't, that's okay too. I'd kind of push you to think abstractly. I'm going to do one more screen share, but I have to have it set up right. So I want to go to Desmos, and let me get it set up. Okay. Okay. So, okay, now I'm going to share. Okay. So here we have the graph. I'll zoom out a little bit and then I'll zoom in. That's the graph of 10 to the x. I have it on a slider, so I could, if I wanted to see the graph of 2 to the x, I could just slide that down. Now I want to write the inverse of x. So what I want to do here is we're going to look at a is equal to 10. So I'm going to look at, I'm going to call it g of x so I don't confuse. The log, I write that as a subscript. And here, let's move things a little bit. You can see how the graph goes. It's pretty much exactly what we came up with. So again, I'll zoom out a little bit. It goes to just as this approaches 0 really, really quickly over here on 10 to the x. For the log, this is going to approach minus infinity very quickly. This will be a horizontal asymptote this vertical asymptote becomes a horizontal asymptote. Now the green looks like it's not rising, but it rises just really, really slow. So I'm going to zoom out quite a bit, and you'll see it's super, super slow, but it keeps rising. Look at the y values. Okay. It looks like it's flat, but really it's not. So, but it's flat compared to the dap. So here, let me show you in a better way. I am going to change the y-axis so it's much bigger. So we're going to go here. So we're going to go to 0 to 1 million to 100,000. And the x-axis is going to go from 0 to million. Let's go to 10 to the 9. Okay. Okay, let's go back to the graph. We're going to go back to home. Oops, sorry, I screwed this up. So you know what? I'm going to end this early.